now we're kind of blowing up the scale in a big way, and we're looking at the whole galaxy. And you guys all did the tutorial last week, and I mean, a lot of this course is just to make you feel really, really small. And we've been talking about stars, and we talked about how stars are so, so far away. But then in the tutorial last week, you would have realized, I hope, that all the stars that we see that have names in our night sky are absolutely super close to us compared to the scale of just our galaxy, right? The galaxy is much, much bigger than what we see, the typical stars in our night sky. So we're seeing what we see with our naked eye is a small portion of the galaxy. And then we'll, of course, learn that the galaxy is much smaller than the universe yet again. The universe is a big place. So we're going to get a sense of what's the scale of the Milky Way galaxy if we can get to the next page. So how we first got an idea of the size of the Milky Way, and then what is the structure of our galaxy, and what is responsible for this structure, how it formed and what produces the spiral arms. And then towards the end, we'll do stuff that's a little bit more mathematical, which is thinking about what is the mass of the Milky Way. So here I have to turn off the lights because these are pretty pictures. So that's what we're all here for. Maybe, maybe not. So here I have a picture of 47, no, that's probably not 47 Tucanae. That I think is NGC 362, which is the globular cluster. We have the Orion Nebula, which some of you may have seen. You can actually see the Orion Nebula with your naked eye, right? That it's a nebula. And this is a great time of year to look. We have the Andromeda Galaxy, which is also you can see with your naked eye, believe it or not. And of course, the Large Magellanic Cloud, which you can see with your naked eye if you're not here, but in Australia. So what do people think our Milky Way's structure is most similar to of these things? And you can, of course, you'll know the answer from what you've done, but you can also maybe think of what the sky would look like if we were in the middle of one of these things, right? Well, that's one of you making that noise. Good. Hearing my computer reboot is suboptimal at this point. So what does it look like? Anyone want to argue for me, like which one they like of these possibilities? Does anyone know the answer? C. Does anyone want to tell me like a common sense reason why it's C rather than, let's say, B? There are galaxies that look like B, and we'll learn more about that a bit later, an upscale version of a globular cluster. What would the sky look like if we lived in B? What do you think? Just imagine you're in there. I think I even have a video of what it would be like in there, but I haven't given it to you, but I have it on YouTube because we made one. So what would the sky look like if you were in the middle of that ball of stars?
B?
Yeah. It would be colorful, okay. But where would the stars be in the sky? Is maybe the key thing to think about. If you're in the middle of a ball of stars, in any direction, you'd see stars, more or less equal numbers of stars. Now let's say if we weren't in the middle of the ball, but off to the side, then there'd be a lot of stars over there, but they'd be in a ball. And we would see the ball over there, and there'd be stars behind us, but more in that round ball. What does the sky look like from a dark place? Where are there stars in the sky? There's some stars everywhere, but there's more stars in a certain part of the sky, which is called the Milky Way. So the stars in the sky, there it says even Milky Way. And why it's called Milky Way is it looks like someone spilt milk across the sky. And it wasn't until Galileo that the Milky Way was resolved into individual stars. It just looked like this white patch across the sky. And that's because the stars are basically in a disk, and if we're sitting in the middle of the disk, we see a white patch all around us, right? So we can infer that structure that it's going to be most like the Andromeda Galaxy, which is a disk of stars, just from the idea that there's this thing called the Milky Way, right? Does that make sense? Does anyone know, it's called Milky Way in most of the Western languages that I know. And even the word called galaxy has the word milk in it. You don't realize that. But if you're a chemist, there's when you, I'm lactose intolerant. Not me personally, but people are always saying that, right? The best things in life are cheese. So, kind of like best thing in life are free. But the word lactose is from milk, and in galaxy, the lac in galaxy is also the milk word. It's the same root, galaxy. And there's an acid, like you might be lactose intolerant. You've heard of lactic acid building up in your muscles. If you're an organic chemist, there's an acid that's sort of like lactic acid that's called galactic acid, which is just something to do with milk, not to do with the galaxy. So does anyone know what the Milky Way is in Chinese? I don't know. No? None of you guys know that who know Chinese. Does anyone know Chinese?
It doesn't really have anything to do with milk.
Yeah, I know. Yeah, what is it?
It's like Silver River.
Silver River. Like in Chinese, lots of things have to do with the river, and I think. So Silver River. So it's the same sort of imagery as the Milky Way. But, that's why I was saying in the Western languages, in Russian, it doesn't sound so nice. It's Mlechny Put, which means Milky Way. Put means path. Mlechny is milk. For what it's worth. I like the Silver River. Over the weekend, I went for dim sum, and I had phoenix claws. You know what phoenix claws are? No.
Like chicken claws?
Chicken feet. But it's called phoenix claws in Chinese, which is much more romantic than chicken feet. But it's the same thing. Silver River, that's lovely. So our galaxy, if we think about what it looks like from the outside, the best guess would be like the Andromeda Galaxy. There are subtle differences between what our galaxy looks like from the outside and Andromeda. I've turned the lights on, maybe prematurely, but the part of the Milky Way that we're most familiar with is the disk of our galaxy, which we can see here, which is what we call the Milky Way or the Silver River, is the projection of that disk onto the sky. And when we're looking out in the sky, if we look out towards, you guys have seen maybe the Pleiades, which is the little seven sisters. So at night, here's Orion, and over there will be the seven sisters. That's more or less looking directly away from the center of our galaxy, but in the plane of the galaxy. That constellation, Taurus, is in the Milky Way. It's in the Milky Way, and it's also in the ecliptic. That's why it's a zodiac sign, Taurus. You can have, I am a Tauran, right? Now, if you think about it, if you're definitely into that astrology, you could infer, if I go to the other side, if I want to look towards the center of the galaxy, which is what's in this picture here, we're looking in the direction of Sagittarius. So the center of the galaxy is in Sagittarius. And we'll talk a lot about Sagittarius A star, which is a radio source in the center of our galaxy, which we believe is where the precise center of our galaxy is, because there's a huge black hole there. And we'll talk about that black hole a bit later. So this is a picture looking towards the center of our galaxy. So we don't get this view in Vancouver very much, because the center of the galaxy is in the southern sky. But if you wanted to see, it won't look like that. That's with a long exposure. But in September or so, if you look towards the due south, you'll get Sagittarius. So it's not from this time of year. In September, look due south near sunset. Of course, now, in March, we could look due south at sunrise, but that's kind of like more hard for most people to do, because no one wants to get up that early. So what people did, starting a bit more than 100 years ago, what they did is they looked in the Milky Way, and we can look at this picture, and what they did is they counted the number of stars in different directions. And they assumed if I see lots and lots of stars, that means that in that direction, the galaxy goes further. And if I see fewer stars in a given direction, the galaxy goes less far. So like maybe an analogy is like if you were sitting in the middle of a forest, well, you don't know if you're in the middle of the forest, and you want to walk out of the forest. So what you could do is look in different directions and count the number of trees over there versus that way. And if I see that there's very few trees over there, I could think, well, maybe there's the edge of the forest in that direction, right? Because I see fewer trees in that direction. I count fewer ones. Does that make sense? That's what they were trying to do. And this was the picture they inferred about the shape of our galaxy. And they inferred that in one direction there are a bit more stars than the other. And but if you look at this Milky Way, it takes up a lot of the sky. It's kind of quite thick, it appears. So they thought that the actual galaxy was something that shape, which doesn't look much like Andromeda. It looks like just a blob, right? It's like blobby. It's a little bit definitely wider than it is thick. It's 10 kiloparsecs wide and 2 kiloparsecs thick. This is what people thought. This is not what the galaxy is like. You saw a picture of the galaxy last week, what we imagine it to look like from the outside, and it doesn't look like that. That's just a mess. It's a mess. And what they did is there was a problem, right? So if we look at our picture of the galaxy that I showed before, you can see that there's lots of dust in the galaxy in different directions. And that makes it hard to see to the edge. So now let's imagine we're in the forest, but it's foggy. But I don't know it's really foggy. So I look in different directions and I can't see trees very far. That doesn't mean the forest is ended. It just means I can't see that far due to the fog in the way. And that's what happened, right? So people, the dust that is in the galaxy absorbing light means that we can't see very far in visible light through the galaxy. We can't see very far. So that's why people thought the galaxy, this is the picture that was shown before, this little black region. So Harlow Shapley, what he did is he looked at not the stars in the plane of the galaxy, but he looked at stars in globular clusters, which are like the picture I showed earlier. And in globular clusters, they're just a spherical ball of stars, and they have stars in them called aurora Lyrae, which are stars that vary in their brightness. And every couple days they vary, and they always have a luminosity of around 100 times that of the sun. So if you see how bright they appear in that globular cluster, that tells us how far away that globular cluster is. Okay? So what he did is he looked all over the sky at different ones of these globular clusters, and he figured out how far away they were from Earth by looking at these stars. So he made a plot like that. So he sees that the globular clusters, they aren't so many to the left, right? There aren't so many that are to the left. There are lots of them to the right. And what he did was he said, oh, well, let's just take the average of where all these globular clusters are, like up and down, right and left. And he concluded that, that's what he would call the center of the galaxy, some point around here, which was well beyond what you could see by counting stars. So it kind of like, whoa, that seemed crazy. So he said, the galaxy is actually really, really much, much bigger than we thought, right? So instead of being sort of 10 kiloparsecs across, which is this thing, he argued that even to get to the center of our galaxy, that was about 10 kiloparsecs away, and there was much more galaxy beyond. So he didn't think it was this little squat thing like this that was 10 kiloparsecs across. What he imagined it to be was a disk that was maybe 50 kiloparsecs across, much, much bigger. Okay? And he did this by looking at these stars. So if we think about where the sun actually is, this was the picture that we had before, but that's not where it is, right? We are actually near the middle of the disk, but a bit above it, and only 1/3 of the way from the center. We're not near the center of the galaxy. We are, if you look at the picture, here's the center, here's this, and we can think we could go way out this way. So we're relatively close to the center, not at the center. So if we think about it mathematically, we're about 8 kiloparsecs from the center of our galaxy, and the whole size of the galaxy is somewhere around 50. So you think 8, half of the galaxy is 25, the other half is 25, and we're 1/3 of the way from the middle towards the edge, right? 8 goes into 25 about 3 times. So why was this way of counting stars the wrong way? I told you why. Does anyone remember? Why didn't it work? The counting stars idea. Why did they think the galaxy was much smaller than it was? What? Yeah, just say it loud. What? Dust. See, I can't pick up the mic if you're like mumbling into your hand. And I might be like hearing the right answer, but you're not saying it. I'm just hopeful. But it's the dust, right? So he relied on visible light. He didn't have infrared telescopes yet, and that was obscured by the dust. Now we have infrared telescopes that you can actually see the stars right in the center of the galaxy. And we'll have even better ones later. Okay? So this is the basic problem with looking at the galaxy in visible light. It's like we're in a foggy forest, and if we look far away, we can't see the trees anymore, right? So we don't know. If you would think this could go on forever, even though I don't see trees in those directions. It's just the light on the way is absorbed. So just to give an idea, like I'm developing a proposal to look at a globular cluster near the center of our galaxy with the new telescope, the James Webb Telescope. And in visible light, the absorption is a factor of 10,000 to this direction of the sky. So the light, all but 1 part per 10,000 gets absorbed along the way. So that's how bad it is, and that's near the center of our galaxy. If you look in infrared, it's like 2 magnitudes, maybe a factor of 2 or 3 is absorbed, not 10,000. So you can really see a lot more by going into the infrared, although they don't look as pretty in the infrared. So this led to Shapley's measurement of the size of the galaxy, led to an argument between these two characters about what is the scale of the whole universe. And why did this make a difference? So at this time, people already had a sense of what was going on, and you looked out in the sky and you saw things like the Andromeda Galaxy, and you saw things like other galaxies, other things, and they were called spiral nebula at the time. They weren't called galaxy. There was a spiral nebula. This was like an elliptical nebula. And Curtis felt that these other objects out there, like the Andromeda Nebula, were galaxies, meaning things like the Milky Way. Keep in mind, like if I use the word galaxy, it has that milk in it. So it's something essentially like the Milky Way, which is an agglomeration of stars. And Curtis felt that the Andromeda Nebula, these spiral nebula, were other galaxies out there in the universe, right? Which made sense, because there are a whole lot of them. When you took the spectra, they look like the spectrum of stars. Now, the problem with this, and one piece of evidence for this, is people looked in these guys and they saw new stars. They saw new stars, nova. And when they saw the nova in these other nebula, those nova were like nova in our galaxy, but fainter. Which would be like, oh, I have our Milky Way is here, and I see a nova, and maybe that other galaxy, it looks like it's maybe 10 times further away than a nova in our galaxy, so that other one is sitting here, and that makes sense. And there are a whole bunch of these little blobs around. Now the problem is, so that's what he said the universe was like. There's a blob that we live in, that's the Milky Way, which is kind of small, 10 kiloparsecs across, and then maybe 100 kiloparsecs away, or a little bit less, 50, would be another one, another blob. And that would be another spiral galaxy. Okay, so that's, and he argued that the universe was full of these things. Shapley, when Shapley went and said, oh, the galaxy is huge, right? That would put these other things that Curtis was talking about would be much smaller than our galaxy, right? Because there was a little blob over there, but it was pretty close. So it led to this debate. Is the universe full of galaxies, like our Milky Way, where each one is kind of small? Or is our Milky Way this big thing, and really it's the only one out there? There's sorts of little scruffy things around that are much smaller than our Milky Way. And so this was the debate. And this is when the universe got really, 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 really much bigger all of a sudden. So spiral nebulae were just gas clouds, and the universe was just one big galaxy with little things that were fuzzy orbiting that one big galaxy. And the sun wasn't near the center of our big galaxy, and the brightness of the novae were similar to those in our galaxy, right? And then they would have different spectra. Now, what Curtis said, Curtis was partially right too, right? So the universe had many galaxies like our own. our galaxy was kind of small. And what he argued is these things in the spiral nebulae were actually inherently much brighter than the ones we saw in our galaxy. So we could push those nebulae a bit further away, so they weren't really part of our galaxy. And that we wouldn't see the light. So he argued that, that there were a whole bunch of, all of these little guys were galaxies like our own, a kind of far away, a little bit further than we think, but they were all small like our own galaxy. Right? And to explain this, he had to have these explosions be something more. I'm going to skip over that. So it turns out both of these points of view were correct in different ways. So the first one was the galaxy is indeed as big as measured by the first person, by Shapley. The universe, the galaxy is this huge place. It's 50 kiloparsecs across. And this guy was right. All those little fuzzy things like the Andromeda Nebula are other galaxies, and they're all about as big as our own. They are all huge, right? So if you were to count now, initially, if you took if we think of Shapley, he would have thought the whole universe was like 100,000 parsecs ball, right? That was it. There was our galaxy sitting in the middle, and there were these little scruffy things around it, and that was it, right? Now we look out, and we have our galaxy is 100 kiloparsecs, and we see millions at this point, now we see billions or trillions, of these little scruffy things out there. So to fit them all in, the universe, instead of being about 100 kiloparsecs in radius, 100,000 kiloparsecs in radius, has to be of order like 1 billion parsecs, at least. That's what they knew at the time. So all of a sudden, the universe, because of this, reconciling these two things, the universe grows by a factor of from 10 kiloparsecs to 1 billion parsecs. If you think of the size of our galaxy, was the initial idea. So the one guy said, oh, our galaxy is a bit bigger. The other guy said, all these little scruffy things must be galaxies like our own. And if you take those two pieces of information, you go from 10 kiloparsecs, a factor of, like I said, 10,000 times larger, no, 100,000 times larger, to 1 billion parsecs. Keep in mind, all the stars we see in the sky are within about 100 parsecs of us. So the galaxy is 1,000 times bigger, more or less, than the stars that we see. And the universe is a factor of 10,000 times bigger than that. So it's pretty big. So our galaxy is one of many, many throughout the universe. So the key thing in measuring the size of the universe and the size of our galaxy relied on stars that are variable. And just to give you an idea of like the names that we talk about, it relied on both of these. So one are called cataclysmic variables, which sounds really bad, and sometimes it's really bad. It can be often, they're usually stars in binaries, and one of those possibilities is a nova, where a white dwarf accretes from its companion and we get an explosion on its surface. Or we can have a supernova, when the star explodes entirely. And it turns out that supernova are maybe 10,000 times brighter than nova, or even more than 10,000 times brighter. So when people were using nova to figure out the distances to galaxies, assuming they were nova, but they were actually supernova, those galaxies, they think, as being close are now actually hundreds or thousands of times further, because the candle that they were using, they were off by a factor of 1,000 or hundreds of thousands. The second type of variable that we talked about are in variables where the star itself is varying just due to its properties. So we have those RR Lyrae variables in a globular cluster, which vary with time just because that's what the star does during that time of its life. But we have other stars that do that as well. So generally, stars that are variable live in a certain region of the HR diagram that I showed here. So the ones that we were talking about, the RR Lyrae variables, typically have a luminosity of around 100 times that of the sun. And they are stars that are consuming helium in their core and then hydrogen outside. So they're horizontal branch stars. And then we have stars that are brighter. They're more massive stars that have also left the main sequence. And those are called Cepheid variables. Okay? And this region of the HR diagram is called the instability strip. It means the stars in this region with this range of temperatures and luminosities are unstable to oscillate. Okay? So if we look at what an RR Lyrae star does, is its luminosity just goes up and down, with a period of about 30 hours or so. And once you've identified them, you can know how bright they are, because all of the stars that have this sort of pattern, sort of heartbeat pattern, they are RR Lyrae stars. So you can, once you identified them as being variable like this, you know they have about 100 suns. So you can see here, the RR Lyraes have periods of around a day, up to around 30 hours or so, but they always have the same luminosity. Whereas these brighter stars, the Cepheids, once I measure the period, I can figure out the luminosity. I need both pieces of information. But these are both standard candles that we can use to measure the size of the local universe, right? So I can see both the RR Lyrae variables and the Cepheid variables in other galaxies that are nearby, and then I compare how bright the one is in that galaxy to one in our galaxy who has the same period. Now I know how far away that other galaxy is. So this is how we build up distances beyond where we can do it with parallax, right? And we have to hook them together, right? So there's some complexities with, there aren't that many of these stars that we actually know the physical distance to, but nowadays we're actually measuring more and more distances to Cepheids because we have telescopes in space that are just designed to measure the distances more or less to about 1 billion stars that are near to the sun. Billion's a lot. That's pretty good. So I have these as questions, but you guys don't like answering questions, so I'm just not going to ask them. So what Hubble did now to actually lock down which of these people were right, Shapley or Curtis, Hubble measured the distance to the Andromeda Galaxy and found, this is about 10 years later, using these Cepheid variables, and found that the distance to the Andromeda Galaxy was much larger than the size of our galaxy. And in fact, the Andromeda Galaxy is about 700,000 parsecs away from our galaxy, or about 2 million light years. Okay? So our galaxy, if you think of it, is sort of this disk that is 50 kiloparsecs or so in radius, and it's sitting here, let's say, and the Andromeda Galaxy is out there about something like 10 times the size of this galaxy is where that galaxy sits, right? So they're relatively close to each other compared to stars, right? If you think of a star, if I had a star the size of a grapefruit here, the nearest star wouldn't be there, it would be far away, like in New York, right? So if you think about galaxies, they are relatively close together compared to their size. So what goes on with galaxies is going to be inherently different than what goes on with stars. Galaxies interact with each other. Like here, we can see there's some galaxy down here. Look at this dude. This is what is he? NGC 205, I believe, which is an elliptical galaxy that's in front of Andromeda. But if you look next to it, you can see, maybe with some imagination, I can see it, there's this trail of stars here, right off the side, that isn't on this side, right? That little galaxy is being shredded by the big galaxy, right? Because they're typically much, much closer together than stars. Okay? So he measured the distance to this galaxy, and that established it and started to establish the length scale of the universe as being much, much larger than people had thought. So we weren't really at the center of the universe. Our galaxy was not the one galaxy in the universe, but there were many of these island universes, other galaxies that were more or less like our own, but billions of them. And our galaxy is a relatively insignificant one, just like our sun. When people realize other stars were just like the sun, our sun is no longer important. But the early 1900s weren't like the early 1600s, so no one got burned over this. It was more accepted at that time, later on. So when we look at our galaxy, there are different parts to our galaxy. And this is now artistic rendering of looking at the galaxy from the side. You can see where our sun sits, about 8 kiloparsecs from the center. And we have different parts. So the globular clusters are more or less spread all around the center of our galaxy in a sphere. And they live in a region that we call the galactic halo, which is just a sphere of stars and clusters of stars that's spherically distributed around the center of our galaxy. The second part that you can see, which is, you might think of it as a continuation of the halo, but at higher density, but it's a bit different than the halo, is the bulge. So that's when you're looking towards the center of the Milky Way. When we look into Sagittarius, you can see that there is this sort of blob of stars that sits there that's like a ball, right? Like as if we lived in a spherical distribution of stars. You can see that there's an excess of stars in the shape of a ball in the center of our galaxy, and that's called the galactic bulge. And what makes it sort of different than the halo, not just that it's more dense, but the stars in there, in the halo, have much fewer elements like carbon and oxygen and so on than the sun, maybe a factor of 100 less. Whereas in the bulge, they actually have more of those heavy elements than the sun. But the part of the galaxy that we're most familiar with is the disk, right? Because that's what we actually call the Milky Way. And what's special about the disk of our galaxy is that's where most of the new stars are forming. And in fact, most of the new stars form not just anywhere in the disk, but in the spiral arms of that disk. Now, it's very hard to visualize where spiral arms are if you're sitting in the disk. But if we look at Andromeda, that gives you an idea of what they... Let's go back a little bit to our pretty Andromeda picture. These things are the spiral arms of Andromeda, where we see these dust lanes, and you'll actually see more bright blue stars near those dust lanes than outside. So how the stars move between these two different parts is different. So in the halo of the galaxy, the stars just move in sort of random directions. So some stars are moving like this, some stars like this, some stars like that. And an analogy is like comets around the sun. They just kind of come in from any which old direction. So these halo stars are moving in crazy directions, and the stars in the disk are all moving around in the same direction, in the plane of the disk, right? Like the planets around the sun, which are all in one plane. Now, if we look at our neighborhood, imagine if there's a star, if we're all moving around like this in the disk, all of the stars will be moving more or less. If we look in the sky, none will be moving very fast. It's like you're on a merry-go-round. And sure, we're moving around and around very fast, but me and the neighboring horse aren't moving very fast relative to each other. Does that make sense? Now, a star in our neighborhood, which comes from the halo, will be moving very fast across the sky. So there are a few stars just in our neighborhood that we think are part of the halo that are just passing through. And one example of that is Arcturus, which is Alpha Boötes. So it's one of the stars in our sky that looks yellow and bright. There are only a couple. One is Aldebaran, and one is Arcturus that we see in our northern sky. So we do have stars nearby that we can study in a long way. Like, for example, in that movie Passengers. Did anyone see Passengers? No? Like, that was the star that they did the slingshot around, if you remember. Like, there was some moment, oh, we're going to go past Arcturus. And that's why you would go around Arcturus, because it's moving really fast relative to stars in our neighborhood. So if you went past it, it would give you a big boost in your velocity, believe it or not. Just like when we're making things around the solar system, you'll go around one planet to get going faster, a gravity assist. Arcturus is a nice star to do a gravity assist if you were going to another star. Maybe we'll have that in the future. So if we think about how long it takes the Earth to go around the sun, we call that 1 year. We can talk about the galactic year, which is how long it takes the sun to go around the center of the galaxy. And that's 225 million years. So we'll use that number, in fact, to figure out the mass of our galaxy within where the sun is. Remember the fact that the Earth goes around the sun in a year and how big the orbit was, that could tell us the mass of the sun. That number can tell us now the mass of the galaxy, and we'll figure that out later in the week. So we left off with getting an idea of the structure of the galaxy, and we'll learn a lot more about what's going on now. There's still a lot of sort of open questions about what's going on. So basically, our galaxy, like most spiral galaxies, has these different components. So you have stars in a disk. The youngest stars are in what's called a thin disk. And then as the stars age, although they're going round and round in this disk, they'll scatter off of other masses. So over time, the older stars are in a thicker distribution, which is here the thicker disk. So if you were to look at stars of different types, for example, like stars that die young, like your O stars and the B stars, they live in a very thin layer along the Milky Way. Whereas stars like the sun, like a G star, they live in a thicker layer. And that's just because on average, the average star like the sun is about 5 billion years old, and it's been going around the galaxy many times. We figured it out, about 25 times. And in that time, it gets scattered around by the gravity of things like clouds of gas in the galaxy. So it ends up having a thicker layer. In the middle is the bulge, which is stars that are typically, there aren't that many young stars in the bulge, let's say. in the very center of the galaxy, near the galactic center, there are new stars forming, which is a bit of a puzzle. But in general, most of the star formation in the galaxy occurs in this thin disk, and in fact, in the spiral arms within the thin disk. And we'll look at some pictures of that. So one way to look through the galaxy is in the visible, of course, the radiation gets absorbed by the dust. But if you look in the infrared, which is this picture, this is around a wavelength of light of 2 microns, hence it's called 2-micron all-sky survey. So the light that we see is around 0.6 microns. That's what we would call yellow light. So this is wavelength that's about 3 times longer. So it could pass, it's less affected by the dust. So we can see now what the sky would look like if we had infrared eyes. So we get a sense, first of all, that the disk is really quite thin compared to its extent. Remember, in visible light, we're seeing things that are closer up. So we see something that appears a bit thicker. This is looking all the way around the sky. Here's the center of our galaxy here. This is the bulge. And if you have some imagination, maybe, it doesn't look perfectly round. I'm sort of tracing like a sort of peanut shape. And that's a hint that in the center of our galaxy, we don't just have a bulge, but we actually have what's called a bar. And I can show you what that looks like in another galaxy in a little bit. You can see even in the near infrared, there's regions here which appear redder, and that's just because even in the infrared, if you have a lot of dust, it will still affect that radiation. So those regions there are places where there's a special amount of dust in our way. So if we look at the outside of a spiral galaxy from the outside, we generally see 2 different things going on. So the one on the left is sort of a regular spiral galaxy, and you can see the spiral structure essentially goes in almost to the center. And what you can have in a galaxy like the one on the left is here you can trace this spiral really quite far in. You might have a big region of stars here called where the bulge is larger, but generally the spiral arms go into where the bulge is and then they disappear. That's one side type. Our galaxy, we think, maybe looks more like this one if we look in the center, that there is a bulge, which you can see here, but also the stars go out in this thing called a bar. And the hint of our galaxy, since we're inside the galaxy, it's hard to tell. But the hint that we have this bar is that in that 2-mass map, things kind of look like that peanut shape is a hint of a bar. Also, if you look really closely, one side of the galactic center has more stars than the other, which is a hint that it's not symmetric, right? So that on one side of the galaxy, the bar is pointing towards us. So we think our galaxy looks something like this, and you saw this in your tutorials. I don't know what's going on. Oh, a text message. Huh. So here's where our sun is, and if we look towards, I guess, the west of the galactic center, so if you thought of our 2-mass picture, if we looked on the left side, the bar is pointing at us. So there's actually more stars on one side of the galactic center than the other, of a given brightness, right? So on the other side, they're further away, so they appear fainter. And that's evidence for that bar that's pointing towards us. So the other thing that's apparent is that the young stars aren't just everywhere, that they're arranged in these spiral arms. you can imagine like how difficult. Of course, if we could come out of the galaxy and look down on it, it would be quite obvious what's going on. So we're in the galaxy, so we have to infer where the spiral structure is, right? So what we can do, so we can infer where these spiral arms are by measuring how much gas is in different directions of the sky. And there are other ways of doing it, but you could imagine it's a hard task since we're sitting inside the galaxy itself. But that's what we think it looks like from the outside. And this bar was something that was only really discovered in maybe the last 15 years. So it's a new thing in the picture. Now, the galaxy indeed ends up being really, really thin. So it's sort of the size of the thin disk going out, where all the young stars are, compared to an extent, is a ratio of about 1 to 100. So there are things in your life that are thinner than that, and things that are thicker. Like a sheet of paper is thinner than 1 to 100. But this is like a DVD or a Blu-ray disc is about that ratio. So, I mean, galaxies are really, really, spiral galaxies are indeed inherently really, really thin, right? So that's maybe a puzzle that we have to understand. So if we look right around the neighborhood of our sun, we're in this part of the galaxy called the Orion Spur, which is just a little baby spiral arm that connects two major spiral arms. And so if we look at where, from our point of view, where different things are, so there's the sun, right? That shows the sun here. And some objects that you will have seen in the sky, sort of the Orion Nebula is over here. And you can actually, if you're good at visualizing, maybe, has anyone seen Orion in the sky? No, surely. You go look out. Has anyone seen stars at night? Okay, good. Orion is that constellation, it has the 3 stars for the belt, and it has a big red star over here, and a blue star down there, and it's like in the southern sky this time of year. It's like the most distinctive constellation, other than the Big Dipper. All right. So you can actually see the Orion Nebula with your eye, just below the belt of Orion. The galactic center is in the downward direction here, and Orion, you can see it's to the left of going away from the center of the galaxy. So the constellation of Taurus, when you look at it, is to the left. Orion is to the left of Taurus, just like in this picture, right? So you can actually sort of feel out where things are. So the Orion Nebula is a region of star formation. So, and it is indeed not in a full-on spiral arm, but this thing called the Orion Spur. What are these other ones here? Rosette Nebula. But if you've not seen the Orion Nebula, I'm not going to worry about you seeing any of these other ones. So the Orion Nebula you can actually see with your eye, naked eye, that it's a nebula there, just below the belt of Orion. Even in Vancouver, in a dark part of Vancouver, you can see it. So, so that's our neighborhood. And so those nearby stars, we can infer their positions even by parallax now. So in this picture, maybe, most of this picture now with the new satellite called Gaia, we can figure out the distances with parallax, so directly. So we talked a little bit last time about how stars orbit the galaxy, and the stars in the disk of the galaxy are basically orbiting in a plane, sort of like the planets going around the sun in the solar system. And we can measure how fast stars move as a function of distance from the center of the galaxy, and that's going to be an important thing that we can use to figure out the mass of the galaxy. On the other hand, the older stars that we call population 2 orbit in all sorts of directions, more like comets in our solar system, for example. So the older stars, for whatever reason, when they were forming, they got velocities that pointed in all sorts of directions. And the stars that formed more recently formed out of this rotating disk of gas. So their orbits look like that. So we're seeing how the galaxy gets formed, like the different parts get formed. Now, if we look at how fast the stars are moving around in that disk, that's what's plotted here now, the distance from the center of the galaxy versus the velocity of the stars. And the measurement is whether it's the velocity of stars or far out, we can see gas going around in a circle. And there's maybe relatively few stars. So this is what it looks like. And, well, there's some weird things about it. So the first thing is, in our solar system, right, we have the sun, who has most of the mass. And as you go further away from the sun, the planets take longer and longer to go around the sun, right? But they also go slower and slower. Their velocity gets less and less and less as you go further away from the sun. You might not have known that, but they do. And it decreases as the square root of the distance. So if you quadruple the distance, the planet will go half the speed as it did. Right? Now, what's shown here in blue is how fast the gas and stars would move if the mass of the galaxy stopped here, so that there's no mass further out. And the key is if you look at the stars and add them all up, and you look at the gas and add it all up, there isn't very much mass beyond that point. There isn't very much mass, apparently, in stars and gas, stuff that we can actually count, see its emission. But what the galaxy does is actually, the stuff is orbiting not only is it not slowing down, it's going faster as you go further out. Which tells us that there's something out there that we don't see. And we're very creative in our naming. So something, well, that must be some sort of matter, and we can't see it, so it must be dark matter. So this is the first evidence in our class, not in historic time, but in our class, where you're seeing evidence for this dark matter. When we look on the scale of the galaxy, even within the orbit of our sun, who sits around here, we say how much mass is required to make the sun to go around in a circle, and we'll figure that out in a little bit. And it's much more than the mass of stars and gas within that region. So there's something else, a factor of maybe, when we add it up, we're maybe only seeing 1/10 of the matter at this scale. Okay? So people first noticed this in the early 1970s for the Milky Way. There were hints of it in other structures, larger structures in the universe. So as structures get larger and larger, the contribution of dark matter to their dynamics becomes larger and larger. In our solar system, we don't see its effects. Okay? So, here's a problem that we talked about a little bit ago. So we see that the galaxy has these spiral arms. And if you look at how the galaxy rotates, at all radii, it rotates at more or less the same speed, right? So what that means is if I'm further out in the galaxy, it takes me longer to go around once. It's just like in a race. Like if you have a running race, and where everyone is in a given lane, right, and you go around the track, the people on the outer lanes get a head start, right? Because it's a longer distance for them to go around. It will take them longer even if they go at the same speed. So here's the galaxy race. If we start with some structure on the left, let's say two blobs, that we want to make into maybe a spiral structure, what will happen is the outer part of the blob will take longer to go around once than the inner part, just because it has a further distance to go. So after a time, it'll look like the next picture. So the inner part of the blob will be ahead of the outer part in angle. And with time, it will get more and more tightly wrapped, as you can see, as it goes over, as it does more and more trips around the galaxy. So here, it's done a quarter turn, right? And then it's done a half turn, and then it's done 3/4. So by the time it goes 3/4 of the way around, the inner part has gone around a few times, and the outer part has only gone 3/4. So that blob now wraps once around the galaxy, right? It wrapped all the way from here, all the way over to there, right? So typically, on one rotation, a pattern like this will get wrapped up quite tightly. So the spiral, if we think about how many times the sun's gone around, it's gone around like 5 gigayears, 5 times a gigayear. It's gone around 25 times. So any sorts of spiral structure that we see, if we put some structure in, it will get washed out by this effect rather quickly. So the spiral structure has to be, for it to be long-lasting, it has to be constantly regenerated. It can't be like, oh, I'm just going to paint the stars some different color, and it'll look like a spiral, and it will for a little while, but then it'll look like a really, really tight spiral and then just wash out. So the spiral structure must be constantly regenerated. So one way of doing this to make spiral structure not be due to some, let's say, pattern that you painted on the stars is to imagine that it's a wave that can propagate through the stars and through the gas. So this is a picture of how one can set this up in a way that doesn't disappear very quickly. So if you, and this is maybe extreme, but let's imagine that the orbits of the stars and the gas aren't precisely circular. And that's what we've drawn here. They're very not precisely circular. They're ellipses here. And if you make the axes of the ellipse not line up, you can see what you can develop is this region where the density is somewhat higher, right? Where the orbits kind of come together, and it's kind of like here. And it looks like a bit of a spiral. See? There's one, and over there. It's one of those things that becomes more obvious if you don't look at it close. Like your brain will see the pattern until you look at it too closely. But for me, I see there's a bit of an excess density up there and down below in the opposite sense. Now, along each of these tracks, this galaxies, the stars and gas go round and round, and on the outer tracks they take longer, and on the inner tracks they take less time. But this structure, if those ellipses don't rotate, will be there forever. So it's not a structure in individual stars, it's in the bunching of the stars as they come through different parts of the galaxy. Now, in fact, this will rotate, but not very fast. So if you set up, rather than, if you set up the spiral structure as a wave, where the density is higher, it can persevere for a long time. For many orbits of the galaxy. So this is, Oh, okay. I wonder if this will work. I hope it works. So this is going to YouTube maybe if I'm lucky. So this shows what the spiral structure, like if we just had that we painted it on, and we have just put stars at different radii and put some extra stars in a spiral structure, but you can see that the stars that are further out go around in the same amount of time as the stars closer in. Okay? So this is not what our galaxy can do. So here's what, if we were to look at with the fact that the inner parts rotate faster than the outer parts. So you can see that spiral gets tighter and tighter and tighter with time. And eventually it'll wash out, right? And whoa, like would you even notice that? And do you see what I mean? And now it's hard to even tell it's a spiral. It just looks like a bunch of rings, okay? Now, if we set up the stars with this funny pattern, you get the stars are kind of on these elliptical orbits. You can see it kind of that pattern perseveres, but it seems to be like always getting sucked in, but it also kind of regenerates, right? So the pattern is still there. I mean, that's completely weird. But the stars are going in and out in there. They're not just going round and round. If I look at individual stars, if I look on the left-hand side, there's stars flowing out and forming that spiral structure on the left. And on the top and the right, the star, you can see like part of the orbit, they form the spiral and then they come back in. That looks freaky. But that's just that picture I showed you there. And then this one is saying, oh, when the stars are all bunched together, we're going to make blue stars and star formation. So we add something else to it. So it's basically that last picture, except whenever the stars are bunching up, we say, oh, the gas is going to bunch up too, and when it bunches up, we make new stars, and those new stars look blue, and then we get something just from that spiral pattern idea. We actually get the stars to form in the spiral arms. So we'll talk a little bit more now. So we have this idea that the spiral structure is formed by where the orbits of the gas and stars make it be more dense, so there's more stars actually there. And also as the gas gets dense, it will form new stars. And we'll talk, I think we talked about that earlier when we talked about star formation. I showed you a picture of gas where we can see the gas flowing through a spiral arm and how the stars are formed in that spiral arm. So this kind of goes all together. Now, we can measure where the gas is, the hydrogen gas, by measuring. Hydrogen has this funny effect that, well, I mean, they all the elements do, but hydrogen is the most common one, so that's makes it very useful. That the nucleus, the proton, acts like a little magnet, and so does the electron, and that's what this is showing. Those little curlies indicate this sort of the spin of the electron, and depending on how the electron is spinning, its magnetic field points in the same direction. So we can have a situation where the proton and the electron are pointing in the same direction or in opposite directions, and because they both have a little magnetic field, there's an energy difference between those two. And when it flips over, it'll make a radio wave at 21 centimeters that we can measure here on Earth and use that to figure out where there is gas in our galaxy. So this shows where the hydrogen gas is, the neutral hydrogen gas, in the sky. So you can see that neutral hydrogen gas is really quite concentrated into this very thin structure. That's the disk of our galaxy. There is hydrogen gas outside of that disk, but that's kind of just spread out over all of the sky. I hope I'm still recording. That would be a shame if I'm not, but that's life. Okay. But in each of these directions, we can also measure how fast the gas is moving. So that's what shows here. So if we look along the plane of the galaxy, we can measure at each direction the velocities of the gas. Some gas is faster, some gas is slower. Just to give you an idea of what you actually measure is in a given direction, you measure how much gas is moving at different velocities, which is what's plotted here in color. So let's just see where we start with galactic longitude. So the center of the galaxy is over here. And if we look at it, we see this sort of pattern here, this sort of sinusoidal pattern, right, like that. And that the fact that its amplitude is sort of always the same tells us that the galaxy, the gas in the galaxy is always rotating at about the same velocity regardless of how close it is to the center. But this is how we can measure how the galaxy is rotating at different distances between us and the center by measuring this hydrogen gas throughout. Okay, so that's how we get those rotation curves. So I'd like to figure out what is the mass of the Milky Way. We've gotten all of the ingredients together. We have the orbital velocity around the galaxy, which is around 200 kilometers per second, and that we are about 8 kiloparsecs from the center. Now I'm going to do this in maybe a slightly different way, using this idea of the galactic year. So that's the time it takes the sun to go around the galaxy. So it's 225 million years, and I just get that by taking this number times 2 pi to go all the way around the galaxy and dividing by that velocity of 200. So I'm going to do this sort of by analogy, because really I don't want to deal with constants like Newton's constant or anything like that. I want to keep my math easy, or as easy as I can. So the Earth goes around the sun once per year at a distance of 1 astronomical unit. And it turns out, this is what Kepler found back in the day, is that if you're going around something, the mass of that thing, you could take the distance to the mass and cube it and divide it by the period squared. So if I were to say go around at twice the distance with the same period, the mass is 8 times larger. That's what that says. Or if I'm at the same distance but it takes me twice as long, the mass is 1/4. And it's just a proportionality. But we can use that now because we know what is the period compared to the Earth going around the sun. So the period is 225 million times larger. And the distance is 1.6 billion times larger. So the distance between the sun and the center of our galaxy is 1.6 billion times the distance between the Earth and the sun, which gives you a sense of how big the galaxy is. So I could just put this together. So the mass enclosed goes as the cube of the distance divided by the square of the period. And this is how I do my math. I can look at the first bits, and 1.6 cubed, you can do it in your calculator if you want, it's about the same as 225 squared. So the two things there cancel each other out. So I'm just left with dealing with the exponents. So on top, I have 10 to the 27, and on the bottom, I have 10 to the 16. Maybe I'll do that. So 27 minus 16 is just 11. I like that kind of math, just the pluses and minuses of two-digit numbers. It looked like it was going to be really hard, but this is how to organize it. So I have 10 to the 11 solar masses between me and the center of the galaxy and that ring. But if I actually count up all the stars and all the gas from their light and from their radiation, I get a number less than a tenth of this, around a tenth of it. So whatever's holding us in the orbit around the center of the galaxy, it isn't the stars that we see. And it isn't the gas that we see. It's something else. It's something else. So, and we can see as we go further out, the velocity doesn't change. It actually goes up. So, in fact, as we go further out, we can conclude that there's more and more mass within those regions. And in fact, the mass within a given region goes as the radius. So if we go twice as far out in the galaxy, there's twice as much mass included in that region, even though we don't see it, right? So as we go further and further out, there's a larger and larger contribution of the dark matter. So we call this dark matter the dark halo. So there's the halo, which is those stars that go round and round the galaxy. The halo does not have much mass in stars, but in fact, the mass of the galaxy is dominated by the dark matter in this halo. And this halo goes well beyond, this 15 kiloparsecs where we sort of are about to run out of stars. And we just call this material dark matter. We have other evidence for, as we go through, we'll see evidence that it can't be normal material, like what's in that periodic table, that just didn't light up for some reason. It has to be something different that we don't understand. But at this point, looking at our galaxy, it can just be, like a guy in a black suit, right? It could be normal stuff, but it just doesn't light up. Okay? So we've not been able to see it in light at all. We only see its evidence from its gravitational pull on other stuff. You could imagine it being dinky black holes that aren't accreting anything. But it's kind of hard to make enough of those black holes over the age of the universe to account for the dark matter. It could be really just stars that are very faint. Right? It could be brown dwarfs, which are failed stars, faint white dwarfs, red dwarfs, which are stars that are somewhat bright, but we don't see them. And those go under the sort of name, the umbrella called MACHOs, which stands for Massive Compact Halo Objects. It's not even that contrived. Now, we can try to measure these MACHOs, because even though those individual objects, they aren't very bright, if one of them happens to go in front of a star, we're over there, here's a star that we can see, this mass goes in between us and that star, we'll notice that star will brighten. The gravity of the MACHO will focus the light onto us, and when we go try to measure that effect, we find that the mass of these objects falls short by a factor of 10 or so to account for the dark matter. So this MACHO thing. There are MACHOs out there, but there aren't that many. There are these type of objects, but they can't account for everything. So the last category is something called WIMPs, which, goes with the MACHOs, and that stands for Weakly Interacting Massive Particles, WIMP. And these are just things that we've not yet discovered. It's like an umbrella term for things that aren't made of the normal stuff that you and I are made of. They're parts of physics that we've not yet discovered, and they just happen to not interact very strongly with other stuff. And in fact, the W in WIMPs means something a bit technical. Weakly means they interact sort of as much as neutrinos interact with stuff. Neutrinos interact through the weak interaction. So it actually means that specifically. It could still be these things, although we keep trying to detect them, but you can always make them more and more weakly interacting. So then you could say they're there, but we don't have enough sensitivity to see them. So here's a picture showing what happens when a macho goes between us and a distant star. So on the left is a star. It's in the middle of the box. It's just kind of sitting there. And when the macho goes in between us and the star, on the right, you can see that the star is bright. And you can say, you could ask, maybe the star just brightened by itself. But how the macho makes the star brighten, it's a very particular feature that is not how stars get brighter and fainter. Usually when a star gets brighter, catastrophically, it gets really bright and then it gradually decays. This thing gets bright gradually and then gets fainter gradually in a very precise way that you can write down the formula. So you can see this, and we see it happening. It's called microlensing. So lensing because it's a type of gravitational lensing, and micro because we only see it as things getting brighter. So this shows you essentially what the curve looks like of brightening and getting faint. It looks sort of like a bell curve, but it isn't precisely that. And as the macho comes between us and the star, it bends the light, so instead of getting one image of the star, we can get 2 or 3 images, which is what we see there. So you get sort of 3 images of the star. One can be bright, one faint. When everything is perfectly lighted up, they're both bright, and then it moves away, and we're just left with the original guy there. Okay? So it doesn't seem to be these machos. So what we can do is look for we could search for WIMPs to just give you an idea of like what a WIMP is like and how it interacts and where people are looking. So in this picture, there are different regions that are, the colored regions have to do with different theories that have a WIMP in them, whereas the lines represent, we've done experiments, and if there was a WIMP above this line, for example, the Edelweiss people would have detected it. And here's another one that goes much more sensitive. Now, just to give an idea of what these mean, on the bottom is the mass of this particle. So they could be more massive, which means there's fewer of them. That's why these thresholds go up. Over here, there'd be fewer of them to account for the dark matter. So there are fewer of them around, so it becomes less likely that our detector will get one. So that's why this kind of goes up. And the mass of the proton on this scale is 1. So it's over here. 10 to the 0 is the mass of the proton. This one is how much they interact with each other. And it's really, really small number, right, that we're constraining. So it says something called a picobarn, which is 10 to the minus 12 of a barn. So this is the particle physicists, they have humor. So like the unit of area is something called a barn. And like you couldn't hit the side of a barn. It means that you aren't good at aiming, right? Because the barn is huge. So in like the interaction of like a neutron slamming into another neutron, for example, is a bar. So that's the size. But this is down by p means 10 to the 12. So these limits mean that the WIMPs interact less than 10 to the minus 20 times how neutrons interact. So you don't, that's that weakly interacting part. They're really weakly interacting. Okay, there you go. So we've talked about this dark halo. We talked about the bulge of our galaxy. We talked about the disk of our galaxy. If we look towards the center of our galaxy, we see a region right in the center that is kind of interesting. So whereas in the bulk of this bulge, there's very little star formation, if we look right in the center of the galaxy, we see evidence of supernova. So we see star formation right in the center. And if we zoom in right to the center, we can see that there's a tiny region that is emitting a lot of radio waves, and that region we call Sagittarius A star. So on the right is how the center of our galaxy looks in different wavelengths. So at the top is infrared, like we were talking about, with 2 mass. The next one down is invisible light, where we can't see very well towards the center. The third one is X-rays. And the bottom is gamma rays. So if we look right towards the center of the galaxy, we see there's lots of gamma rays. We also see this funny thing right in the middle at the galactic center. And if we look right there in the galactic center, this is kind of fun. You can look at the individual stars. So in the infrared, we can look at individual stars in the galactic center. And this is actual measurements over the course of sort of 15 years or so. Oh, how the Earth moves. That's not so interesting. Can we go back? YouTube. Okay, oh, well, that's even horrible. There's a commercial. Oh, with what's his name? You go up in space and then you start doing commercials. Play the guitar a little bit. So if you look, they're orbiting something, but there's nothing there, right? And over the course of a few years, they're orbiting that object. And their orbits are absolutely massive, and we can figure that out. We're going to get rid of you football guys. The other one was nice, right? So they're all orbiting, and that video, they conveniently drew a little star in there. So that's what all of those objects are orbiting some other object. And again, we're going to do the same game that we did for the mass of the entire galaxy. We can figure out the mass of that object that they're orbiting using the same technique. Here, though, it doesn't take geologic time to see that guy orbit. It orbited in 15 years, that star, that closest star in that light with the yellow orbit. And the distance to that region in the center of the galaxy is 8 kiloparsecs. And they're measuring, it's absolutely amazing, the precision of those measurements. It showed on the picture the scale. Like that entire picture there was about 1 arc second in size. So like from the ground, that would be like the image of a star blobby. But they can, using adaptive optics, zoom in on there. And so that orbit is just a tenth of an arc second in size, or about 800 astronomical units at that distance. So we can do the same game as before. We have 8 cubed over 15. That's the hard math. 8 cubed, I don't know what it is. 512, I believe. 15 squared is 225. So if I divide that, I get a number like 2. And then I'm left with what remains, the 800 and the fact that I have a 1 year on the bottom. So if I do that, I find that that mass is 2 million solar masses. There isn't 2 million solar masses of stars there. They wouldn't fit in such a small ball. Would have to fit under that little star, right? So in the center of our galaxy, there's a dark object, doesn't emit any light, that's very little light, that's very, very compact, that is around 6 million solar masses. And that is the black hole in our center of our galaxy. Right? So that's the black hole, a supermassive black hole in the center of our galaxy. And as we talk later in the week about other galaxies, this is something that is generic to big galaxies. They all have really massive black holes in their center. And in fact, our galaxy's black hole is one of the real small ones. So they go from around a million solar masses up to several billion solar masses. So we can think about now putting everything together in a sort of cartoon of how the galaxy formed. So we imagine at the beginning there's a cloud of gas that has some sense of rotation and it's being pulled in under its own gravity. It's just like scaling up star formation, but now on the scale of a whole galaxy, if you remember. The thing will collapse, and in star formation, because it's spinning, it will form a disk eventually here. But this is on the scale of a galaxy. So as that thing is collapsing in on itself, there'll be regions within it that are somewhat more dense that will collapse in on themselves within that region and form stars. And it's from those little pockets within this big gas that were more dense, we form bunches of stars, and those are these guys that we see now as globular clusters. Now, there may be some stars that form just in the middle of nowhere, and those form the halo stars, or with time, as these globular clusters fly around the galaxy, they'll leak stars. Stars will escape from them, and they'll just be flying around the halo. And so we see stars in globular clusters. We also see stars from the halo, like Arcturus, that are escaped from the globular cluster. Okay. So as time progresses, this gas keeps collapsing, but since it has angular momentum, it can't collapse directly as a sphere. It forms a disk, and that's where the gas is now, more or less, in this disk. So the later stars that form in the disk of our galaxy.